Welcome back viewers to the second part of the series of videos on adherent points, limit points and isolated points. This video does not aim to provide any analytical explanation. Rather, we are going to introduce some types of sets which are frequently used in studying analysis. As usual, in this video too, we are using some shapes just to make things easy to understand. Before we proceed, it is advised that please watch the first part of this series on adherent points, etc. because this video uses concepts introduced earlier and therefore watching the earlier one will help you understanding the contents of this video in a smoother way. Now let us proceed. Suppose we have a set F in a metric space E. This set F may have isolated points, and as we know, such points are necessarily contained in the set. However, some of the limit points may lie outside F. We want to see a situation when the set F contains all its limit points. Let us see it more closely. Now we see the situation of limit points. These points may be interior points of the set or boundary points of that set. But we know that interior points are always elements of the set, whereas the boundary points may not be elements of the set. So when we say that the set F contains all its limit points, it has the same meaning as saying that all boundary points lie in the set. That is, the boundary of F is a subset of F. But we know that a set is closed if it contains its boundary. This we have already learned in earlier videos. So it is easy to conclude that F is a closed set if and only if F contains all its limit points. However, a more practical way of saying it is that a set is closed when it has no limit points outside the set. By this way of understanding, we also cover those sets which have no limit points. Let us take example from the standard metric space of real numbers. If we take F to be an open interval with endpoints 0 and 1, then we know that 0 and 1 are limit points of this set. But obviously 0 and 1 are not elements of F. Hence F is not closed. But if we take F to be a closed interval with the same endpoints, then it contains the limit points 0 and 1 and therefore it becomes closed. Let us see another situation when, in addition to being closed, all the points of the set are its limit points. Here, set F contains all its limit points and therefore it is closed by earlier discussion. But there may be situation when F contains some isolated points too. However, we are avoiding that situation here and we assume that all the points of F are limit points. In such situation, when a set is closed and all its points are its limit points, we call the set as a perfect set. For example, in the usual metric space of real numbers, a set F consisting of just two numbers 0 and 1 has no limit point outside F. In fact, it has no limit point and therefore it is closed. But its members 0 and 1 are not its limit points and so it is not a perfect set. So for being a perfect set, you need two things. First, the limit points of the set should be member of the set, and the second that the elements of the set all the elements of the set should be the limit points of the set. Now let us see this situation in another example when we take F to be a closed and bounded interval with the endpoints 0 and 1. Then the only limit points of this set are the elements in this interval. Therefore, it satisfies both the conditions of being a perfect set, that is, it is closed, as well as all its points are limit points, and therefore it is a perfect set. Let us now proceed to observe another situation when all the points of a set are its isolated points. This type of sets may have limit points or they might not have limit points. Such sets are called discrete sets. Let us again consider a set S in the usual metric space Rd. Here, the set S on your screen is certainly infinite and countable, whose elements are ordered and can be marked in such a way on the real line that each element can be separated from another element with the help of open intervals. Therefore, all the elements of S are its isolated points. Obviously, this type of sets cannot have a limit point. Let us further have some observations of this situation. Here you can easily notice that finite sets do fall in this category. That is, all finite sets are discrete sets with no limit points. We also have countably infinite sets falling into this category, such as the set of positive integers or the set of integers on the real line. These sets are also discrete sets with no limit points. It means all the elements of these sets are its isolated points, and therefore the sets are discretes. They also don't have any limit points. Now let us see an example of a discrete set with limit point. On your screen, the set S containing 1, half, 1 by third and so on has 0 as a boundary point. This we already know from earlier videos. But 0 is not an element of the set. Hence, we have a point which is a boundary point but is not an element of the set. So certainly that point is a limit point of the set. Hence 0 is a limit point of S. You can also observe it in another way. You can see that every open interval centered at 0 will certainly contain some point of S, and therefore 0 becomes a limit point of S. However, when we include 0 as a member of the set S, then an element 0 of the resulting set S hat is limit point of S hat, and hence S hat ceases to be a discrete set. So S is a discrete set, but S hat is not a discrete set because S hat contains a limit point. Lastly, we are going to introduce dense sets. Let us suppose that F is a set in a metric space ED. Let us imagine a situation when E shrinks completely to F, meaning thereby that all the points of E are adherent points of F. In such a situation, F is called dense in E, or we say that F is a dense subset of E. Clearly, in this situation, all the points of the full metric space E are either the interior points or the boundary points of F. We also try to reiterate the same statement in another forms for your convenience. We may say that F has no exterior points to reiterate this concept, or we can also say that all the points of the full metric space E are either an element of F or a limit point of F. Another version could be that the complement of the set F is either empty or does not contain any other point possibly except for some limit points of F. In all these situations, we call F to be a dense set in the metric space E. In the end, we now see that the set Q of rational numbers is dense in the standard metric space of real numbers. In our earlier videos, we have already seen that the interior of Q, that is the set of rational numbers, is empty, whereas the boundary is the full metric space R. We also note that for every real number alpha, the open interval with endpoints alpha minus R and alpha plus R, where R is any positive number, contains infinitely many rational numbers. So, its intersection with Q minus the singleton containing alpha is clearly not empty. Therefore, by the definition of limit points, every real number, that is, all the elements of the metric space R, is a limit point of Q. And therefore, we may conclude that Q is a dense subset of R, or Q is dense in R, or Q is a dense set in R. So with these all discussions, we are finishing the contents of this video. In the next video, we shall be further talking about adherent points, limit points, etc. Till then, take care. Bye.